Hi guys, today I'm going to talk about the influence lines of the Müller-Berslau principle, and this is actually quite a nifty technique to find the influence lines, and you will actually find it quite easy. Once you start down that path, you will hardly ever use the methods that we described in the previous class. So what is the Müller-Berslau principle? It states that the influence line for a function, be it a reaction, shear, moment, axial force, is to the same scale as the deflected shape of the beam when the beam is acted upon by that function. Okay, so what do I mean by that? So let's say I want to find the influence line for the reaction, and let me call this, let's say, the reaction at A. So he says when the beam is acted upon by the function. So what we are going to do here is we are going to remove this support. Okay, so now this is free to move, can go up and down, right? Or even you can stretch it this way if you want to, because this is a hinge. So with that, I'm going to again, this is 1 kilonewton is at a random point. So I'm going to allow this to move. So I'm going to move this 1 unit delta y in this direction because of this AY. So the reaction is here, and the reaction is going to move this portion of this beam upward. Okay, so I'm going like that. Now, since this is now going to become one piece, right? So it's going to move and it's going to pivot on the roller here. As this is moving up, so is this 1 kilonewton. So this now is going to be a value, a deflected shape, a deflected value, a deflection of delta y prime, right? So since the beam is in equilibrium, correct, and therefore it does not move, right, then the virtual work sum must be equal to 0. So if this is my virtual deflection, which I made equal to 1 unity, then AY times that is going to be equal to 1, right, times this deflection right here, delta y prime, which is equal to 0. Since this is 1 unit, then AY is equal to delta y prime. Interesting. So this value, okay, of the reaction due to this load right here is equal to the value of this deflection right here. Okay. I'm gonna apply that for the shear. So at the shear, since this is intact, I'm gonna now remove this and put what we call a guided roller. So this is now able to move. I'm going to apply the shear. Again, I'm going to apply this in the positive direction. So this is going downward clockwise and this is going upward clockwise. So it's like I'm dividing the beam into two pieces, this piece and that piece. Okay, so again, this is going to be pivoting around this support, and this part is going to be pivoting around this support. I'm going to do this move delta y, so that total movement is equal to 1. Again, I'm having this 1 kilonewton here that's just sitting there, and as I'm moving this up, this is also going to move up by some value delta y prime for the same reasons. Equilibrium, virtual work must sum to 0. Then the shear force VC times this one must be equal to that. Then VC is equal to delta y, which is the same result that we got for the reaction. Applying the moment, for me to be able to move this, right, or to make to this function C, so I have to make this equal to 0, and the only way for me to making the moment equal to 0 at this point is by introducing the internal hinge. And I'm with you, once you remove a support, the structure becomes unstable. Once you add the guided roller, again the structure becomes unstable. Once you add this internal hinge, the structure is becoming unstable because it's allowing me to move. Okay, so again, this is a fictitious movement, right? So here, imagine that you're putting your 2 fingers right here and then lifting this up. So I'm lifting this up. Remember, now I have 2 pieces. This is one piece and this is the other piece. And think of it like a ring. Okay, so as this ring is going up, right? So these 2 connected to it are allowed to move while they are still pivoted at these supports right here. So I'm going to keep this movement until I'm getting the change in this angle equal to, you guessed it, 1. Okay, then again, due to the equilibrium conditions, mc times 1. Well, again, this 1 kilonewton here is going to go up delta y prime, then mc is equal to delta y prime. So that is what he meant. So if I want to influence line, let's say for reaction, I go and remove that reaction, allow it to move. The deflected shape or the resulted deflected shape is my actual influence line. Okay, so let's do this. I want to find the influence line for AY. So what I will do, and we call this qualitative because I'm not giving you actual values. Okay, so it's qualitative and there's quantitative. Quantitative means you are giving me values. So now I'm just considering qualitative value. This is now A. Again, remove A, add the load, go up 1 unit, and then we know that B is 0. So this probably will be your influence line for AY. If I want to draw the influence line for BY, I'm going to remove BY, allow it to move, apply the force, move again 1 unit, right? And this is not going to move, obviously. So again, this whole thing is moving, so this is going to be like that. So again, here I only have one piece, and here's those drawings in a, I guess, nice way. Now let's look at this one. So here I want the influence line for AY. So obviously I'm going to remove this, right? And then I'm going to start to move this 1 unit. So what's happening? Again, this is one piece. So as you're moving this one piece, right? So this is going to move with it like that, correct? It's going to pivot on B, right? So my resultant deflected shape is going to be like this. So this is still 1 unit, okay? Because again, I am removing this. This is still one piece. So as you move this up, so this is going to go up as well. Now, if I'm using the influence line, if I want the influence line for BY, again, I need to move what? I need to move this guy right here, allow this to move up. Again, here I have one piece, but here what you've noticed is that this one piece is pivoting on what? It's pivoting on this reaction right here, A. Okay, this is A. Sorry about that. So as this is going to move, right? So since this is going to pivot, then think of it more like a seesaw. Okay, it's moving around this point. So because I'm keeping this intact, it is one piece. Okay, let me erase that because I'm going to give you the, I guess, the better version of this. Okay, so this is, again, this is the only value that we know. I don't know this value, but I can get it if I know if I know these dimensions, right? If I know these distances, I can get this value. But since I'm not giving you these distances, so I'm just interested in what the influence line or the shape would look like. Okay, so that's what I mean by qualitative. I only know this movement, the 1 kilonewton, because I already know that. And again, if I know these instances, I can very much find this ordinate right here using triangle similarities. Okay, moving on. Now, if I have a fixed end reaction, I want the reaction at AY. Again, I'm going to allow this to move, so I'm going to use this as a guided roller. So as I'm pushing up, I'm going to push that whole piece up, right? So this is going to be like this. It's going to be constant. Now, if I'm going to do the moment, now the moment, again, I'm going to introduce this internal hinge. But again, as you've noticed, this internal hinge is within this fixed moment. So this internal hinge can move. So if I want to put my fingers right here and start lifting this up, I can't. Okay? It's not moving. So the only thing that I have is now, because this part here from this part can actually move again like one piece. So obviously, if the only way it has, it's going downward. Okay, so this now is going to be my influence line for. So think of it as like falling under the influence of gravity until this value reaches 1. Okay, again here I'm using positive moment nomenclature. Okay, to get that. By the way, this value is going to be negative. Okay, so this is negative moment, and we know for fixed end, right? If you have a fixed end then or cantilever, then this value is going to be maximum here, which is going to be a negative value. So again, just going back here, put in a guided roller, allow this to move up, okay, because that's what you're doing. The ring, you're trying to lift this up, you can't, then this piece is just going to fall down if you want to look at it that way. Or at least that's how this is helping me, I guess. I'm just going to erase that because I have those done in a neat way. Okay, so this is the influence line. Again, these are qualitative reactions. Moving on to shear. Again, I'm going to remove this shear and introduce a guided roller like that. So now this is going to go down, right? And this is going to go up. Again, this cannot move, B, because this is fixed at the supports, and this is also fixed at the supports. So as this is going down, this is going to go like that, and this is going up, this is going to go like this. Now that total movement, okay, is going to be equal to 1. So, which is what I did here. Now we know this is going to go all the way up to 1 kilonewton, so through similar triangles I can find this to be B over L, and again this is going to 1 kilonewton, so this is going to be A over L. You will always find for the shear, again this is negative shear and this is positive shear as a rule. When you draw the influence line for shears using the Berslau law, again use it more like a shear type action. This goes up and this goes down, okay? And then this instance is just going to be this A divided by L, and that's just going to be B divided by L, and just what I did over here. Some other examples. Let's draw this at C. Again, here what I'm going to do is I'm going to use the positive shear, right? So I'm going to make this go down and then this go up. So obviously this only can go up this way since it's pivoting like that. So that's going to be for this piece right here. So again, I have two pieces, right? This is the second piece. Now the second piece here is going to go down, but it's not going to move due to the support. So as this is going to go down, so this is going to go up. So now that would be your influence line for the shear at C. If you go the influence line for the shear at D, again here I'm going to introduce this guided roller, right? I'm going to go up like this and like that. So what's happening here is what? So now this actually, there's nothing preventing this. So this is actually can just free fall, right? And since the total movement has to be equal to 1, so that before that, this cannot move because this is pivoted here and pivoted here. So this piece actually cannot move at all. So this value is going to be 0. So the total movement of 1 is actually going to be translated here. So this is telling me that the influence line of D, as long as I have a force here, I'm getting a shear. Once I go beyond that point, there will be no shear at D, which is kind of obvious because after that point, there's going to be no load. Again, let me take this out and show you how they look like. Again, this is what we call the quantitative. I have no values. I know this whole thing is equal to 1. This I already know is equal to 1 because this has 0 movement. Okay, moving on to the moment. Here, again, using the same technique, I'm going to introduce internal hinge. Now I'm having two pieces, piece AC and piece BC. Put your finger right here and then go up. As you do, these are free to move. They're going to pivot right here and then they're going to pivot right here. Now I said this value is going to be equal to 1 radian. So if I wanted to know this value, if I want to call that x, so we know from triangles that if I call this theta 1 and this theta 2, then this angle here 1 must be equal to the summation of the two angles except the one next to it. Okay, so that's going to be theta 1 plus theta 2. Now tan theta 1 actually is going to be x over b, right? And tan theta 2 is going to be x over a, with the only unknown x. And from that I will find that x is going to be equal to ba over l. Okay, so again, just repeating what I did. Here are the equations. These are the values for the moment. So you can see how easy that is. Now if I'm going to do influence line at moment MC, for instance, again, introduce internal hinge, lift this up. Okay, this is going to go up. and the second piece is going to pivot around this. So that would be the influence line for my moment at C. D, I'm going to use the same thing. Introduce this internal hinge, try to lift this up. You can't, then this is just going to fall down, with this again being equal to 1. Let me get this out again, and here's what I talked to you about. Okay, so these are the influence lines, the quantitative influence lines for the moment at C and D. Now, how I'm going to use this? So I have two cases. One, when I have only a concentrated force applied to the beam. Okay, so for any concentrated force acting on the beam, truss or frame, the value of the function can be found by multiplying the ordinate of the influence line at the position multiplied by the magnitude of the force. So like I said, on the influence line diagram, all that I'm saying is, let's assume I have the influence line for the reaction at A, and let's say I want to know if I have a force of 50 kilonewton. Okay, so let's say this is 2 meters. Again, this is 1, right? And this is after 1 meter. So this ordinate obviously is going to be 1/2. So if I apply a 50 kilo, so what would be the value of the reaction AY if I apply a 50 kilonewton at this position here? So in this case, AY would be equal to 50 times 0.5, and the answer would be 25 kilo in Newton. Okay. If I put, let's say, a load here, all I have to find is what is this value of this ordinate, multiply 50 by it, and it will be the value of the reaction due to that 50 kilonewton load. Okay. Uniform load, on the other hand, instead of dealing with the ordinate, I will deal with the area under the influence line multiplied by the intensity of the uniform load. So let's say I have a uniform load of 20 kilonewton per meter, for instance. Then the reaction AY would simply equal to the area 1/2 times 1 times 2 times 20. Okay, so that will give you the value of Y, which is going to be 20 kilonewton. Okay. Right. Again, easy. 20 times 2, 40 divided by 2. That's 20. And let me show you how we are going to use that. So here, he's asking, determine the maximum positive moment that can be developed at point D due to a concentrated moving load of 16 kilonewton, a uniform moving load of 3 kilonewton per meter, and a beam weight of 2 kilonewton per meter. So the beam weight obviously is going to be constant all over, because it's the beam weight. The only thing that's moving is the 3 kilonewton per meter and the 16 kilonewton. So for me to find the maximum positive moment, obviously I need to find the influence line for MD. So again, I'm going to use the method of Berslau. I'm not going to use X and Y and all that. So probably at this point I'm not going to do that. So since I want the positive moment, or since I want the influence line of MD, I'm going to introduce again that internal hinge at D. Now what you've noticed, this is one part. Now this is the second part because of this actual internal hinge of the existent internal hinge. I need to put that here. So we're having 1 part, 2 part, and 3 parts. So think of it as like the straight lines connected to linkages. Okay. So I'm gonna again use the same technique. I'm gonna put my hand here and lift this up. Okay. So as I lift up, so this piece 1 can only go up this way, right? Since it's pivoting at E. Now C wants to go up, correct? Because it's pivoting at C, and because of the presence of this internal hinge, now this piece can move. Okay, so as this is moving up, this obviously, because this has no control, right? Because now I'm controlling everything through this guy right here. So as I'm moving this up, this is going to go down. So as this is going down, obviously this is going to go down with it. So this is the influence line for MD. Okay, so guess what? Just recreating what I did up there. Now, since he wants to know what the actual moment is, I actually need to figure out what these values are. Again, we know that this value is going to be equal to 1, right? So if I'm assuming this as being h, my unknown, then my 1 is going to equal to what? H over 4, right? Plus h over 2. Okay, so I'm looking at this triangle right here and this triangle right here. From that, I will get h equal to 1.33. So if I know that this value now is 1.33, I can easily find this value, right? So if I'm taking this triangle, so again, this divided by 2 must be equal to this divided by also 2. Since this is negative and this is positive, so this value will become also 1.33, but in the negative value. Okay, and I think I did that for you in a neat and nice way. So now since I know these values, so this is now the positive value and this is the negative. He wants what? He wants MD positive. Okay, that's what he wants, the maximum positive moment. Let me just erase that. Okay. So I'm going to use that to show you how I'm going to place the load based on the okay. Now, so let's do first of all the concentrated force. So the concentrated force, the maximum value for the concentrated force is actually at D, right? So here I'm going to put in my concentrated force, correct? Because this is giving me the maximum ordinate of 1.33, and I want the positive, so I'm going to put that here. Also, this is also a maximum value, but that's negative, so that will give me a maximum negative moment, but he's not asking me for the negative moment. Okay, then the other part also would be, I know that I have the beam weight, so the beam weight I actually have no control over that, so this is going to be the distributed load for the beam weight. Okay, then becomes the live load that I have, and as the term live load means, I can position that anywhere. So for me to get the maximum area, I'm going to position that on part CD. So this is now going to be, excuse me, this is going to be my live load. Okay, so if I position the load in this way, I will guarantee you will get a maximum positive moment at D. So using the equations, then I have the 16, so this is my 16 times 1.33. Now I also have at this position here the 3, which is coming from the live load, right? So that was 3 and the kilonewton per meter, and that was the 2 kilonewton per meters. So the total is going to be 5. The area is going to be 1/2 times 6 times 1.33. Now this is now negative area, so I'm going to put the value of negative, right? So that's going to be -2 times 1/2, 4 times 1.33. So the maximum positive moment is going to be 35.91. Don't believe me? Position the load as such and find the moment at D through what we used to do in the past. And you guys, this ends this class. You have a nice day and stay safe.